All right, so now we're going to talk about the convergence of a generalized one-step method. Okay. So let's recall it's like some pieces of the puzzle, if you will. It's like the first thing, of course, is the local error. The local error, which is at time step h, with some initial condition z bar, is defined to be the difference between the numerical flow by one step. It's like of step size h with respect to the initial condition z bar, okay, and the difference between that and the exact solution flow, again, applied to the same initial data, okay. And in general, it's like what you find. So this is the local error. It's like, and what we saw, it's like before, it's like, for example, with the trapezoidal rule, and more generally, it's like most one-step methods, is that this local error, okay, has some sort of bound that the error norm is bounded by some multiple, it's like of h to the p plus 1. So some c z of h to the p plus 1. Okay. All right. Let's say z bar. Okay. And then you further suppose that there are some constraints. It's like about the extent to which the numerical method depends on the initial data it's being applied to. So we assume further that there's some sort of Lipschitz continuity, that the numerical method, again with time step h, applied to two different pieces of initial data, right, satisfies some sort of Lipschitz continuity, which depends on the time step. Okay, so this is 1 plus h L hat. Okay, and then there's a norm which measures the difference between the data. Okay, and in general, it's like this L hat may or may not, it's like be the Lipschitz constant of the original dynamical system. Okay, so in general, L hat is not the same as the Lipschitz constant for the vector field. Okay, so I should say that in this sort of abstract setting, it's like there, of course, it's like some estimates it's like you need to establish for your specific one-step method. But once you've formulated in this way, it's like then you can apply this sort of general framework for proving the convergence of the one-step method. Okay. Okay, so in any case, with those assumptions, it's like in mind, then what you have is the following. Okay, so then you can look at the error. Okay, so the error at the nth plus first step, of course, is defined to be nothing more than the difference between the numerical solution, it's like at that time, it's like at the corresponding exact solution at that time. Okay, so that's called that Zn plus 1, okay, minus Z at Tn plus 1, okay, numerical solution and the exact solution. Okay, so by definition, of course, it's the numerical solution is obtained by applying it's like successive applications of the numerical one-step method, and of course, it's like the exact solution can be obtained by applying successive sort of exact flow maps, if you will. Okay, so that's what we're going to do in the next stage. All right, so we're going to write this as the numerical flow map applied to the solution at the previous time. And then we're going to write this z at tn plus 1. It's like in terms of the exact flow map applied to the solution at the previous time. So, okay. All right. So we've not really done anything so far. And then the next thing you do, so the problem, of course, is that when you have something like this, this term has a different flow map and it has a different initial data. Again, so in order to actually establish the estimate and to bring to bear some of the things which we sort of assume, you need to do the usual trick of adding and subtracting terms. Okay. So, so we're going to add and subtract a term which looks like the numerical method, okay, the numerical one-step method, but applied to the exact solution, okay. So we're going to add and subtract a term like this, and you'll see why it's like that makes your life easier. Okay, so so I'm going to look at the error norm now. So the norm of the error at the n plus 1 time, right, is equal to the norm of the numerical flow applied to the numerical solution at time tn. Okay, and then I'm going to subtract off, it's like this term, which is the numerical flow map applied to the exact solution at time tn. Okay, and I'm going to add it again. And then subtracting off, it's like now the exact flow map at tn. Okay. So now you have two pairs of terms, if you will. You have this pair and this pair. And if you look at this pair, now the flow maps, the numerical flow maps are the same, and the only difference is in the initial data. Okay, and so what that should sort of evoke in you immediately is this estimate here, which says that the numerical method applied to different initial data satisfies this kind of Lipschitz continuity condition. Okay, and then you have this second pair of terms which have the same data, but it's the difference, if you will, of two different methods. And that again should evoke in you, it's like this estimate we have for the local error, which again is the difference between the numerical flow map and the exact flow map with the same data. Okay, so now it's like you can apply the triangle inequality. Well, okay, so you can apply the triangle inequality to this. Okay, and then we can apply the estimates, it's like which we have. Okay, so this first term is bounded using this estimate here in terms of the Lipschitz continuity of the numerical method, right? So this is 1 plus h L hat, the difference between the data it's being applied to, right, which is Zn minus Ztn. And of course, it's like you should recognize that this is nothing more than the error at the nth stage. Okay, and then you have this term here, which involves essentially evoking the local error estimate. Okay, so this is C at Z at Tn. Okay, h to the p plus 1. Okay. Okay, and so now it's like we have an error recurrence which looks like the following. Okay, 1 plus h L hat, the error at the nth stage, plus some constant. let's just call it C bar. So I'm going to, it's like assume that you can essentially find a uniform bound. It's like on this constant here, and I'm just going to denote that by C bar, and then I have big a term which is h to the p plus 1. Okay, so now I have this. It's like the error at the end plus first stage is some amplification, or the error at the end stage plus some, it's like term which is coming from the local truncation error. Okay. So if you recall, it's like when we discussed the convergence of the Euler method, when you get to a stage like this, the next thing you do is that you evoke the discrete Grunwald inequality. So we'll talk about that in a little bit.